And here we start 7.5, everyone's favorite sum and difference identities. Getting started here with seeing what works, what doesn't work with other types. 3a plus b. We can distribute in a 3. That's a multiplication property. We will get 3a plus 3b. That one will work, no problem. If I plugged in anything for a or anything for b, that one will always be left side equals right side. That identity is true. Second one, a plus b squared. Oh, a scourge upon humanity on this one. So many people want to distribute in that exponent. You cannot do that. A plus b squared is meaning a plus b multiplied by itself, a plus b. Which would, if we expand that now, expanding is a distributive property, a multiplication property. In that case, we would have a squared plus 2ab plus b squared. We can easily prove that that is not true by picking some test cases. So in this case, let's just use 1 and 1. Does that equal, let's work left side, right side. 1 plus 1, that's 2 squared, that equals 4. And the other side, 1 squared plus 1 squared, that's 1 plus 1, that equals 2. Oh, those do not equal to each other, so this one, no go. How about for logs? Let's check that out if this is true. Log of a plus b. Well, that kind of looks similar to one of the rules we did. Well, let's just stick with 1 and 1. Log of 1 plus 1 as opposed to log of 1 plus log of 1. Log of 1 plus 1, that's log of 2. Punch that into your calculator. You get approximately 0.30. But log of 1 plus log of 1, the log base anything of 1 is always 0 plus 0. That equals 0. Hey, that doesn't equal either. That one's a no-go. How about sine of a plus b? Can we just distribute in the sign? Well, let's just stick with 1 and 1. So sine of 1 plus 1 as opposed to sine of 1 plus sine of 1. Running out of room, sorry. So that's sine of 2. Sine of 2, plug it into your calculator, you get about 0.91. Sine of 1 plus sine of 1, you get 1.68. Those are not the same. That one's a no-go as well. Moral of the story here. We can distribute a number, but you cannot distribute an instruction. Log, instruction. Squared, instruction. Sine, instruction. That's a function. You can't distribute a function, but you can only distribute a value, a number. But these work when we have sine of a plus b. Sine of 30 plus sine of 60 is going to equal all that mess right there. And all we're doing is verifying. Plug it into your calculator, prove that it works, or use the unit circle. I'm going to use the unit circle. I'm just going to do the first one, that's all. Sine of 30 plus 60. Hey, that's the same thing as saying sine of 90 degrees. Sine of 90 degrees, going to the unit circle. We're talking right here. Oh, that's sine y value. That's equal to 1. Other side. Sine of 30, cos of 60, cos of 30, sine of 60. Let's see what we do there. Back to the unit circle stuff or special triangles. Picking off our 30-degree triangle, our 60-degree triangle, we need sines and coses from there. And sine of 30, hey, that's 1/2. Cos of 60, that's 1/2. Cos of 30, that's root 3 over 2. And root 3 over 2. 1/2 times 1/2, that's 1/4. Root 3 times root 3, that's the square root of 9, that is 3. 2 times 2, that's 4. 1/4 plus 3/4, oh, that's 4/4. That's 1. Look at that. Left side equals right side. Good idea to be able to verify the other ones as well. Here's your formulas on your formula sheet. Looks like that. You don't got to memorize them. You have to know when to use them and how to use them. Really what the whole point of this lesson is going to be, just to give you a heads up now. On our unit circle, we went to 30, then 45, then 60, then 90. Our first break was 30 degrees. Then it was 15, then it was 15, then it was 30. Hey, wouldn't it be nice if we could go 15 degrees, stop all the way around? That's what this lesson does for us. It allows us to go and stop at the 15 and at the 75. Now, for those of you who want to see the proof of these, I can go through with you. Come in, talk with me, and we can talk about the geometry behind proving those. So for most people, we're going to move on and we're just going to talk about how to use them. The sum and difference identities can be used to determine the exact values of some sine and cosine ratios. Exact values. That's talking about those 15, 75. So any multiple of 15 degrees now is going to be able to be used as exact values. As you can see there, sine is 75. 75, that's broken up into 45 plus 30. 75 was not on the original unit circle, but two values that are 45 and 30 can be made into 75. So now because we're talking about sine, we're going to use the sine equation, the sine formula. And because we added two values, we're going to use the adding of a plus b, or alpha plus b. Substitute in. Wherever you see an alpha, you put 45. Wherever you see beta, you put 30. Hit our unit circle. Put them in. Sine of 45, that's 1 over root 2, or root 2 over 2, whichever one you prefer. So if they use 1 over root 2 in their answer, this is what the answer would look like. If you use root 2 over 2 in your answer, it'll just be a rationalized version of that. So you'd have root 6 over 4 plus root 2 over 4 equals root 6 plus root 2 over 4. Notice in both of these, and it's always going to happen, you're always going to get common denominators when you work through these. You don't have to worry about common denominators. The fractions will always add nicely. And there's your bit.ly link for today. Which one is going to be able to represent the cosine of 105 degrees? Now, just thinking back to that one that I just went over. The sine of 75 degrees. I didn't need to use 45 and 30. Are there any other two values on the unit circle that you could add or subtract using to get 75 degrees? Find another one that works as well and work it through for yourself. All right, this one right here, we're going to star this question. You're pretty much guaranteed that a question of this type is going to show up for you on the diploma. It's so important, I'm going to let the lady explain the other one for you, the one that they did.
Given angle alpha in standard position with its terminal arm in quadrant 2 and cosine alpha equals -5 over 13, and angle beta in standard position with its terminal arm in quadrant 1, and sine beta equals 3/5, determine the exact value of cosine alpha minus beta. I'm going to use the identity cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. I know that cosine alpha is negative 5 over 13, so I can substitute negative 5 over 13 for cosine alpha. Sine beta is 3/5, so I can substitute that here. I need to determine cosine beta and sine alpha. I know that the terminal arm of angle alpha lies in quadrant 2, so I can show that on a diagram. Cosine alpha equals negative 5 over 13. Since cosine alpha equals x over r, I can say that x is negative 5 and r is 13. Sine alpha equals y over r. I've already said that r is 13, but I need to find y, which is the height of the triangle. I can use the Pythagorean theorem. X squared plus y squared equals r squared. Now I can substitute x equals negative 5 and r equals 13. Negative 5 squared is 25. 13 squared is 169. 169 minus 25 is 144. So, y squared equals 144. This means that y is the square root of 144, which is positive or negative 12. Based on my diagram, I know that y is positive, so y equals 12, and sine alpha equals 12 over 13. I can replace sine alpha in my equation with 12 over 13. The terminal arm of angle beta lies in quadrant 1. Sine beta equals 3/5. Since sine beta equals y over r, I can say that y is 3 and r is 5. Cosine beta is x over r. I know that r is 5, but I need to find x, which is the length of the base of the triangle. I'll use the Pythagorean theorem again, and substitute y equals 3 and r equals 5. 3 squared is 9. 5 squared is 25. 25 minus 9 is 16. So, x squared is 16, which means that x equals the square root of 16, which is positive or negative 4. I can see that x is positive, so x equals 4, and cosine beta equals 4/5. I can replace cosine beta in the equation with 4/5. Now I just have to simplify. Negative 5 over 13 times 4/5 is negative 20 over 65. 12 over 13 times 3/5 is 36 over 65. Negative 20 over 65 plus 36 over 65 is 16 over 65. So, cosine alpha minus beta equals 16 over 65.
All right. I know she did such a great job. You probably don't need me to do this one, but I'm going to do it anyways just because I enjoy it. So let's get started. First of all, our first angle, cosine alpha. And we are told that it's in quadrant 3. And they might say, they might give you the domain to say which quadrant it is. They might tell you some other information, about some other sine value or cotangent or something like that, just to give you the information to say it's in quadrant 3. We're going to do a quick sketch. It's right over here, quadrant 3, and cos is x over r, so x is negative 3. R always has to be positive, so we know the x is negative. And then we need to find y. So y squared equals 5 squared minus negative 3 squared. 25 minus 9. And that gives us 16. That's y squared. So y is either positive or negative 4. And we know we're going down, so we're taking the negative 4 this time around. Good. Got all parts on that. Let's go to our second angle. Let's put here that was alpha. Label it. Next angle, the beta angle. All right. Sounds like a fraternity here. We got the alpha house, the beta house, and we're looking here. We're in quadrant 2. And there we go. Y over R. So then our y value is 1. Our r value is always positive. It's 3. We need to find the x value. Same thing. X squared equals 3 squared minus 1 squared. So, oops. 9 minus 1. There we go. And that gives us 8. That's x squared. So x is equal to the square root of 8. And we look at the diagram. Yep, we're using the negative one of that. So negative root 8, which is really 2 root 2. So either root 8 or 2 root 2, whichever one you want to use for that. Now we go to what we're asked to do. Sine of alpha plus beta. So sine of alpha plus beta is equal to, looking on the formula sheet, scanning through, oh, it is sine of alpha cos of beta plus cos of alpha sine of beta. And all we do now is we look at our two diagrams. We've got our alpha, we've got our beta triangle, and fill in the information from there. So sine of alpha, sine is y over the r, and cosine is x over r in our yellow triangle. And our beta, cos, was x over r. Sine is y over r in our blue triangle. Fill it in. And so we got negative 4/5 multiplied by negative root 8 over 3 plus negative 3/5 times 1/3. And again, notice we always get the common denominator, so that's a nice thing. And I'm actually going to change right now this to just negative 2 root 2, just because I'd like to use the simplified version. And we get 8 root 2 over 15 minus 3 over 15. So we've got 8 root 2 minus 3 over 15. Done deal. That is the exact value of that, of sine of alpha plus beta. Now there's also the sum and difference of tangent. Well, that's just made up of sine over cosine. So we substitute in. Looks like lots of fun. Divide the numerator and denominator by cos alpha cos beta. Simplify it up. And we get the next one, which you are going to be able to use. And that right there is sitting on your formula sheet. You just have to be able to use it. So you've got your sum and your difference identities. All right, question number 2. Let's simplify it. Means, hey, work backwards. Notice we've got those the same. We got those the same. That's meaning that's alpha and that's beta. Okay, hey, look on your formula sheet. Which one does this most resemble? Oh, look at that. It represents sine of alpha minus beta. So we just plug it in and say sine of, oh, the alpha was 8x minus 3x for the beta. 8x minus 3x, oh, that's sine of 5x. Done deal. For this one, scan through, see which one of those it most represents. And that is an alpha, that is a beta, that is an alpha, that's a beta. Oh, look at that. This is tan of A alpha plus beta. And let's just plug her in. So tan of alpha plus beta gives us tan of, now we just add that, 1/6 plus 1/12, common denominator, 2/6 plus 1/12, oh, that's 3 pi over 12. 3 pi over 12, that reduces, that's pi over 4. Oh, we've got a number. I can figure out tan of pi over 4. That's 1. Okay, another use for this is something that shows up quite often, is prove that this is true, or be able to use some type of this form here. Let's start on the left side. This is our alpha, this is our beta. So that means we've got on the left side sine of alpha cos of beta minus cos of alpha sine of beta. And then we go to our unit circle, sine of pi, hey, that's 0, cos of x, minus cos of pi, hey, that's 1, sine of x, I get 0, minus, oops, sorry, that should have been a -1, cos of pi is -1, 0 minus a -1 sine of x, oh, that's sine of x, left side equals right side. And final question, bringing solving back into the identity section. Whoa, I want to solve that algebraically, because graphically I just punch in my calculator. Well, they say, oh, hey, I've got cosine, sines. This might be one of those. And sure enough, if I look carefully enough, I've got alphas and betas, and on my formula sheet, that's cosine of alpha minus beta. Looks very similar to that, where alpha is 4x, beta is x. So I can just simplify it to this. Cosine of alpha, 4x, minus beta, x, equals 1. So now I've got cos of 3x equals 1. Ah! We've done these already. We're going to treat it just like the 3x is just a regular x. Again, we're talking from 0 to 2 pi. I'm going to expand my domain by multiplying everything by 3. 0 to 3x to 6 pi. That means I get to go around 3 times around unit circle. All right, once, twice, 3 times around. And let's pick off our unit circle part here. I want to know where is cos equal to 1, and cos is equal to 1 right here on the unit circle. That's at 0. But we get to go around 3 times. Be careful, look at this. I don't get to hit the last one on that 3rd time. So 3x is equal to 0. That's my first one. And then it's going to go around again. And that's going to happen at 2 pi. That's once around. I get to go around, second rotation around. That means it's going to happen again at 4 pi. And then I get to go around a 3rd time. But uh-oh, I don't get to use the 6 pi. 0 on the first one, 2 pi on the second one, 4 pi on the third, or sorry, 0 and 2 pi on the first rotation, 4 pi on the second rotation, 6 pi on the 3rd rotation, but no go on that, baby. We're stopped here. But this is at 3x. I need to deal with that horizontal stretch, which is a horizontal stretch by factor of 1/3, meaning I need to multiply all of my answers by that stretch factor of 1/3. So x equals 0 over 3, that's 0. 2 pi times 1/3, 2 pi over 3, and 4 pi over 3. Boom. Done deal. All right, answer those ones up. In class, I'm going to bring you in some other little tweaks and ways that they use this concept on your exam. Have a good one.